video, we want to evaluate the triple integral of z dv over the region E, which is bounded by the cone z equals square root of x squared plus y squared, and the sphere x squared plus y squared plus z squared equals 2. So to solve this problem, we want to convert to cylindrical coordinates. And so let's begin. First, we know that x is equal to r cosine theta, y is equal to r sine theta, z is equal to z, and then dv is equal to r dz dr d theta. So let's draw this out. Let's figure out the bounds. So we have a sphere, and then we have a cone. We want to find basically the integral over this region. And the region we're interested in is over here. So above, so if we say that this is the, pretend this is the z-axis here. Above is the sphere. And then below is the cone. So the question is, can we write these equations in terms of polar? Starting off with the cone, we know that z is equal to z, and then x squared plus y squared is r squared. So we have z is equal to square root of r squared. Well, square root of r squared is just r. And so that's how we get z is equal to r. The sphere, x squared plus y squared is just r squared. So that's why we have r squared plus z squared equals 2. So to evaluate this integral, the lower bound is going to be the cone, like we said, which is z is equal to r. And then above it is going to be the sphere given by r squared plus z squared equals 2. But we want to solve for r. Oh, sorry, we need to solve for z because we're going to do, we said, z r dz dr d theta. So remember, this is just dv. And so the limits for the first integral is going to be in terms of z. It's going to be z equals. So on the bottom is z equals r because that's the cone. And on the top is the sphere. So you need to solve for z over here. So we'll subtract by r squared and take the square root to get z is equal to square root 2 minus r squared. Okay, next we want to solve for r. R represents the radius. So to figure out what r is, we want to set those two equal to each other. So you want to see where the cone and the sphere intersect. So for that, we start off with r squared plus z squared equals 2. We know that r is equal to z, so I'll just plug it in. R squared plus r squared equals 2. We have 2r squared equals 2, r squared equals 1, and so r is positive 1. So r cannot be negative because it's a radius. So therefore, the r ranges from 0 to 1. And then finally, we want to look at theta. Theta is just going to be, just going to be looking around. Like if you're looking above the z-axis, you'll see that in the plane, it's going to be, we're looking around 0 to 2 pi. So that's the integral that we're interested in. So that's over here. Now let's evaluate this integral. So first we're going to integrate z r in terms of z. So that's going to be z squared over 2. And then the r, we can just multiply later. So we plug in square root of 2 minus r squared first to get 2 minus r squared over 2, minus plug in r for z, get r squared over 2. And that simplifies to just 1 minus r squared. Then remember, we need to multiply by r. So it's going to be r times 1 minus r squared. That's over here. And we want to integrate this from 0 to 1. To do that, we first want to distribute the r to 1 and negative r squared. Find the antiderivative. Plug in 1, plug in 0, and subtract, and get 1/4. Finally, we want to integrate 1/4 between 0 and 2 pi. And that's just going to be 1/4 times 2 pi, which is pi over 2. So the final answer is going to be pi over 2.